Hi everyone, and welcome to another video from Eric's Electronics Workbench. So on the bench today I have this Omega MML 400 DC power supply. It was manufactured by Lambda. Now this is a switch mode type power supply, and it's rated to a maximum output power of 400 watts. Now these power supplies could be configured with different types of output modules. So this power supply has the type G and the type C module, but there are numerous other modules with different types of output voltage ranges and current capabilities. So this type G module is adjustable from 12 to 24 volts at up to 15 amps, and the type C module is adjustable from about 5 volts to 12 volts at up to 12 amps. But again, it's good to 400 watts total. So for example, if this was set to 24 volts and you were drawing 15 amps, that's 360 watts, so it would only leave 40 watts available power on the type C output. So as long as you don't exceed the 400 watts, then there's no problem whatsoever. Now, this has remote voltage sensing on both outputs. Other modules had some additional features. This has an unused area over here that some additional features could be installed. So the power supply was very modular and could be custom configured, when it was ordered from the manufacturer. Now, unfortunately, this power supply has developed a problem. So let's get started with the troubleshooting and check it out. So the fault with this power supply is that it won't start up correctly. So sometimes it'll start up and operate for a short amount of time and then it powers back down, and other times from the get-go it won't start up at all. And what I notice is that when it's not operating correctly, this cooling fan is kind of stuttering and rocking back and forth. But I don't think there's anything wrong with the fan motor, because at the same time the voltage on the output terminals is very unstable and it's very low. It's not within the normal operating range. So I think the motor just doesn't have enough voltage to operate correctly. Now, I wasn't sure if these output terminals had an over voltage protection on them, so there's an adjustment for each of the output voltages to adjust within the range of the modules, and I've adjusted that. It didn't make any difference, but now I don't know where these are set, so I'll demonstrate the fault and what it's doing. I'll get it connected to the digital multimeter in just a moment. But if it does power up even briefly, the output voltage will just be some random value within the range of these modules, because again, I don't know where they're actually set at this point. So this power supply was obviously meant to be installed in a piece of equipment. It's not a benchtop power supply. So I have the power cord connected over here, but there is exposed AC line on these terminals, so you need to be cautious of that. See the terminals right there. And there's a jumper link right here for the 120 volt operation. See the ranges that are marked on there. So if you're operating on 240 volts, the high voltage input, you would remove that jumper. So if you're following along, you're absolutely doing so at your own risk. If you're working on a switch mode power supply like this, you need to be using an isolation transformer, and if you're probing around inside the power supply, you should use an isolated ground oscilloscope, something like a fluke scope meter, because you don't want to cause a ground connection within the power supply. You have to remember that there's a lot of circuitry on the input side that's directly connected to this AC line. There is no isolation from this line. That's why, of course, you need to use an isolation transformer. And remember, an isolation transformer doesn't protect you from being shocked across that AC line. There's still a voltage potential that will be a very nasty, if not lethal, shock. What the isolation transformer protects against is contact from the AC line to ground. So that's where it's adding that protection. Now that gets into a whole other topic with isolation transformers and so forth, but just know that you do need to be using that. But if you're unfamiliar with the safety precautions in working with a power supply like this, please refrain from doing so, because there are no second chances. Very, very high voltage in here. If you come across the wrong point in this power supply, that could be the end. So be very, very cautious and take care. And again, if you're working on something like this, you're doing so at your own risk. So let me get my digital multimeter connected over to these terminals here, and I'll power it up and just take a quick look at what it's doing. Like so. All right, here we go. Alright, so about 7 volts, and you kind of hear that ticking sound that it's making. The voltage is very low, kind of wandering all around there. Definitely not right. That ticking sound, I'm not sure if that's maybe just the fan motor that's making that noise, or maybe it's the transformer in here that's having current pulses applied to it. In some ways, it kind of reminds me of a fault protection where it's trying to start up and then shutting down, then trying to start up and shutting down. So, if a component failed and it's going into this kind of unusual mode, or is it truly trying to go into protection mode because of some kind of fault? I'm not really sure. So let's take a look over here at this other output. Let's go across there, actually go like this. work. Got to stay there. Stay. There it goes. Okay. Try it one more time on the other output. Oh. That won't work. Let's try this one more time. There we go. Okay. And you can see same kind of little ticking sound with very low voltage, 2.5 volts or so. So definitely not correct. If I take the power supply and just stand it up like so, power it up one more time and you can probably hear that ticking sound. You hear that? So that's obviously not doing a whole lot at this point. So the next thing that I'll do is get this top cover removed and let's take a look at the inside and start the troubleshooting. Alright, the top cover is removed, but the fan is still attached because there's some adhesive sealant on this connector that I didn't remove yet. I may need to do that eventually. And this ground wire was just attached to a lug that was on the top cover over here, so I've removed that so this could be positioned out of the way. So the power supply looks very clean inside. Just at first glance, I'm not seeing any components that look damaged or overheated, but I'll look at them a little bit closer in just a moment. So before I start on any further troubleshooting, I should take a quick resistance reading across the output terminals and just make sure that there's no short circuits, because if there's a short circuit, it could certainly go into an overcurrent protection mode. So let's put that over to resistance and just take a quick reading across here. So no problems there. That looks okay. About 725 ohms, 726, no problems with that. The other output looks like it charges up a little bit, probably a capacitor across the output, and that levels off about 316 ohms. So no issues there. Those values look fine, so I'm not seeing any direct short circuits across the output. So let me get you zoomed in just a little bit closer here. You can see the general layout inside the power supply. So the AC line comes in over here on that terminal board. There's a fuse for some protection, some filtering going on over here. And then the AC line is passed into a bridge rectifier, which is down on the bottom. It's on a heatsink over here. And that rectifies the AC line to DC, and then it's filtered by this large bank of capacitors. So that bridge rectifier is configured in different ways depending on the high or the low voltage setting with this link that's over here. So at that point you have a high voltage DC, and that high voltage DC is switched at about 100 kilohertz by this probably a power FET or a MOSFET that's on this heatsink. There's actually two of them. It looks like there's another one down below. And you have to be careful because this heatsink could possibly be electrically live when this is in operation, so you never want to touch an exposed heatsink like this. Certainly would want to measure it first and see if there's any voltage potential on it. But nonetheless, these are driving that high voltage into this transformer, switching it very high rate, 100 kilohertz. And the whole purpose of a switch mode power supply is to get this transformer down to a very small size. So this is a 400 watt transformer. A 400 watt transformer that would be 60 hertz would be much, much larger. So the higher the frequency, the smaller the transformer, the smaller the magnetics. So the output of this, the secondary side, is connected to this circuit board across here. And then it looks like these modules are just attaching to the circuit board. So very clever design, because these modules could be changed to different configurations, but it looks like the rest of this is probably always the same. It doesn't change. There might be some slight adjustments or changes that were done, but the general layout wouldn't really change that much. So you can see these large bus bars that go back into here look like they attach to the circuit board. So this board, it has an insulator back here. You can see right here. So we'll have to remove all of this, but that's just protecting this board from the back of the power supply. So it should be able to get in here and then probably separate things. So I'll have to take a closer look at that and see how this all comes apart. Now, thinking about what the fault is and where we should start the troubleshooting, there's obviously a lot going on in here. You can see there's a lot of surface mount components all over in here. I'm seeing a lot of surface mount components all over this board. So the fuse is not blowing. So there's not likely to be a short circuit or a problem with these capacitors or the rectifier circuit or anything like that. It looks like a startup problem or a fault, maybe a protection that it's going into. It could possibly be on these modules. So removing these modules and then maybe trying to power up the rest of the power supply. You know, it might be a way to isolate and see if there's any issue going on over here. This fan, what I'm noticing though, is that it plugs into the circuit board here, but the output is taken over here. Now this output could be configured many different ways depending on the modules, but the fan is always getting its voltage off of this board, and the fan doesn't want to run. So I'm wondering if the problem could actually be on this circuit board, because the voltage on this board isn't even correct because it can't operate this fan. If the problem was over here, I would think this board would have the correct voltage and the fan might run, but the voltage out of the power supply would be incorrect. What it looks like to me is that because we have basically very high frequency AC on this board coming over to these modules, there has to be rectification and regulation going on over here. There's a lot of components on here. There's definitely some regulation and control going over here. There's remote voltage sensing inputs, things like that. The voltage adjust on these potentiometers right there. So these modules look like basically self-contained regulation circuits that are just taking a high frequency AC and then converting it down to the DC and coming out on these terminals. So to me it really points like the problem could be over here. This bottom board, I see some components, mostly filters. There is an electrolytic over here, but definitely some electrolytics on this board. Always suspicious of capacitors. If you've seen other repairs that I've done, capacitors always tend to be a problem. They're always the first thing to look at. I'm not seeing any capacitors that are bulging or any leaking capacitors in here, so that's a good sign, but it doesn't mean that there's not necessarily a problem. If these capacitors have an issue down here, maybe it's affecting the voltage, but those can be tested, so this board definitely needs to be removed. You can do some testing here. But to do any work on this board, it's probably going to need to be removed. In fact, I see an electrolytic down here that even to get to the back of this board, this transformer is in the way. So looks like there could be a fair amount of disassembly to even get in here and start the troubleshooting. So let me start removing some of these components and kind of doing some measurements in here, and I'll do some work and I'll be back in a little bit. Alright, I had the two output modules removed from the circuit board, and as I was taking a closer look at these various sub-assemblies and how they're interconnected and how the power supply functions, I noticed something different about the design of this switch mode power supply compared to a typical switch mode supply. So in a typical switch mode power supply, you have optical isolation from the output of the power supply back to the input, and that is part of the voltage regulation setup, but the optical isolation is necessary because you don't want any direct connection from this portion of the circuitry, which has direct AC line connections, over to the output of the power supply. If there would be a fault or something like that, you could have a direct AC line connected to the output terminals. It would be a very, very dangerous situation. Now, in this power supply, there is no optical isolation used whatsoever, and in fact, there's no connection from these modules and the output voltage back to this section over here. So if we take a look at this right here, you can see this is the secondary of this transformer, and looking down here you can see this circuit board is definitely completely separate from anything over on this side. So we basically have the isolation is just physical distance right there, and we have the secondary of this transformer is of course completely electrically separate from the primary, so that creates the isolation that we need. But again, there is no optical type feedback. And if we look at these modules here, you can see on this circuitry on the top right here, some op amps, a lot of passive components, resistors, capacitors, and so forth, but all of that circuitry is self-contained and in no way is connected back to this circuit over here. So basically this is acting like a frequency converter. You have the 60 Hertz AC line coming in, and it's being converted to about 100 kilohertz AC over here. And then these modules need to rectify that and then regulate it. So again, I think these are completely self-contained, and it probably is pointing to the fault being over in this section over here. So I'll continue with the disassembly, and I would like to remove this board, take a closer look at it. Looks like a fair amount of disassembly with some desoldering and so forth. So I'm going to start on that next, and I'll be back when I have some updates. So you might be thinking, wait a minute, don't disassemble and remove this circuit board without testing these components over here. Obviously, these are the easier components to get to. Well, actually, I already did that, and I'm not seeing any issues with any of these capacitors. So these are large electrolytics. There's another smaller electrolytic that's down, kind of tucked away in there. And everything is looking okay. Inductors are fine. There's some diodes down there that are looking okay. So all of those components were easily tested from the backside of this board, but not seeing any issues there. Now I do see a problem right over here on this bottom board, but it's not related to the problem this power supply is having. I'll grab my flashlight here, but look what they had to sneak into the power supply. We have 2 REFA capacitors right there, and those are safety capacitors, and they are in really, really bad shape. They are completely cracked and on their way out. So they haven't gone up in smoke yet, but they will if they're left in there. So a little bit hard to see right now, the cracks that are in those cases, but when I remove them, I'll show you a little bit closer. But if you're not familiar with what a safety capacitor is, or the REFA brand and the problems that occur with these capacitors, I did an entire video on failing REFA safety capacitors, so definitely check that out if you're not familiar with that problem. So I'll get those replaced, but the next thing that I'll do is remove this circuit board, and we'll continue with the troubleshooting. Okay, this circuit board and this entire assembly was removed from that circuit board by desoldering these pins right here. So 3 right there, 2 there, and then these 2 over on this side. But take a look at what I found so far. So on this board in the corner over here, there's a small electrolytic capacitor, and it kind of has a film or a scum around the circuit board, kind of a buildup. And at first I didn't think too much of it, and I don't know if it'll really show up on the camera or not, kind of hard to see. But I was thinking, maybe it was just a residue from flux or something on the board, but it's really not present elsewhere. Now the fan runs over on this side and blows air across, and the dust and stuff kind of accumulates over on the side. There was some dust on these heat sinks, but I think maybe this electrolytic has leaked. And if you look at one of the traces on the board right here, there's a little bit of, I would think, corrosion that's setting in. It has some discoloration to the trace that isn't present anywhere else. And when these electrolytic capacitors leak, they definitely cause corrosion. And aside from all of that, if we take a look at this tester here, just turn this around this way. So I will take a reading on the back side right here. And look at that. So the tester tells us that we have open circuit or low capacitance. And this capacitor is certainly in a value that this tester should be able to read. Try it one more time, just to double check. Nope, and there it goes again. It's the same result. So that capacitor definitely needs to be removed off the circuit board, and we'll test it out of circuit and just double check it. So that's very suspicious. That may be an issue going on there. Now, there's another electrolytic right here, and get that a little bit closer, you can see. And unfortunately, the back side of the board is hidden by this transformer, so I can't get to it. But just looking at the traces that are on the board, I think I know which traces this capacitor connects to. So if we take a reading around it here, like this, I think one side of that capacitor is on this resistor, and I think the other side is this group of traces right here, and I think it goes to this pad right here. Okay, and that gives us the result of 23 microfarad at 2.2 ESR. So not too bad. I mean, that's not an indication of a faulty component. And this actually is, let's see what the reading is on the side. It is marked as a 22 microfarad, 35 volt. So the capacitance is certainly within reason. Now, given that the age of these components is exactly the same, and if this one is faulty, this one I think needs to be replaced as well. I don't see any point in leaving it in the circuit. So there's 4 screws right here, and if I remove those screws, I think this transformer can be moved away from the board just far enough to desolder this. The leads on the transformer are right over here, so I don't think I need to desolder those. They're not pins, they're actual wires that come out from the windings, so I think there'll be just enough room to sort of tilt the board and get in there and work a little bit. But my first thought is if I replace this capacitor and then maybe try and test the power supply and see if it makes a difference or not. And I can probably put the power supply back together enough without putting it back in the case to be able to test it. So let me take a look at that. The first thing I'll do is remove it from the circuit board. We'll take a reading off of the board, and then if it looks bad out of circuit, I'll go ahead and get a replacement. All right, the small electrolytic capacitor has been removed, so let's test it out of circuit. Yeah, same result. So open circuit, low capacitance. So that capacitor has definitely seen better days. So I'll get a replacement installed, and then we'll go from there. Now I also removed those two safety capacitors. So if we take a look at these, let me get you zoomed in a little bit closer here. So if I can get the light to reflect here, see those cracks in the housing or on the case right there? It's kind of those lines that are going through the side. And on this one, I don't know, one side I think was a little worse than the other. Yeah, you can see right there, see those lines going through. So what's happening is the case of these capacitors with those cracks is allowing moisture to get inside, and then the internal material starts to disintegrate and fall apart basically, and is no longer a capacitor, and it turns into a resistor. It starts to pass current, and then it overheats and ultimately just goes up in a cloud of smoke. So these are known for that kind of a failure, where they get the hairline cracks. That's the first sign that they're on their way out. And these look pretty typical when they're at this stage. Sometimes they'll get a kind of a bulging top to them, and then after that they just, like I said, they go up in smoke. And boy, when they go up in smoke, they let out a huge cloud of smoke. So these are Y-class capacitors. You can see on the top right here. So right there it says Y2. So that's the class of safety capacitor. And then the value right there, 4.7 nanofarad or 4,700 picofarad. So I'll get some replacements of these capacitors. I may have them on hand, so I'll check. If I don't, I'll have to get them ordered in. But I'll get those installed as well. So anytime you have an electrolytic capacitor that has leaked, you need to thoroughly clean the circuit board. So that little capacitor was installed right there. So I'll thoroughly clean this board and get all of that residue off, because the residue is actually electrically conductive. So you don't want any of that on the board, and it also causes corrosion. So I'll get this all completely cleaned up and ready to reinstall that new capacitor. The two new electrolytic capacitors are installed on the circuit board. So you can see this one right there, and then the other one right there. Now this side of the circuit board has a very close fit to the capacitors that are mounted on the lower circuit board. So this replacement capacitor was a little bit taller than the original, so it had to lay over on its side so that it would fit. So no issues with that. I just formed the leads before I soldered it in position. These are the type that I had on hand for the replacement, so that'll work perfectly fine. So these replacement capacitors are Panasonic brand, very high quality, 50 volt, 22 microfarad, 105 degrees Celsius rated, and the originals were 35 volt, 22 microfarad, 105 degrees Celsius. So when you're replacing a capacitor, you always need to go with an equal or higher voltage rating, within reason. And the same capacitance value, don't change that unless you know what effect it would have on the circuit. And the temperature rating should ideally be the same, but you could upgrade it. If it's 85 degrees Celsius, you could upgrade to 105 degrees Celsius. You don't want to decrease the temperature rating, especially in a power supply where there's elevated temperatures. Now I needed to desolder the primary on this transformer from this circuit board. Previously in the video I mentioned trying to just tip this board and then I'd have access to the bottom to desolder this capacitor, but that didn't work. These wires are too stiff, especially these two over here. These are very fine wires over on the other side. It's a little bit closer so you can see it. So I just desoldered those. I didn't want to risk damaging that transformer or the windings. So now what I need to do is reassemble all of this so that we can test it. So I'll put everything back together again, and I'll be back when I have it ready to go. All right, all the sub-assemblies of the power supply are together, so let's see if it's come back to life. So I have the fan plugged into this circuit board, power cord is attached, the digital multimeter is connected to the output of that module, so we'll monitor for any DC voltage there. Now I don't have the two safety capacitors installed. They're on order, but they're not here yet, and that won't affect the testing at this point. So let me plug this into my isolation transformer, and let's see what happens. Here we go. And that's unfortunate. It doesn't look like it's working. So the voltage is fluctuating around. Definitely not at the right value. The fan is just kind of shaking back and forth. It's not powering up correctly at all. So really no change whatsoever. Go ahead and unplug that from the isolation transformer. Well, that's too bad. That's interesting that this capacitor had no effect, even though it was leaking and basically an open circuit. So let me take a look at the power supply some more, think about the next steps for troubleshooting, and I'll be back when I have some more ideas. So check it out, the power supply is now functioning. So you can hear the fan is running, and look at that DC voltage coming out of that module, and it looks like a very stable reading as well. So I started thinking maybe there's a thermal fault. What if there's a component that's become temperature sensitive, or a cracked solder connection, something like that going on. So if you heat up or cool down the circuit board and the components, sometimes that can reveal where a fault is at. So I had my heat gun handy, and I thought, well, I'll just warm up this general area over here. Now, not so hot that you're melting solder or damaging any components, but I just gently warmed this area. I didn't warm these modules over here, so just concentrating on this area. And then I plugged the power supply in, and it powered right up, no problems whatsoever. So now, of course, the question is, where is the actual problem? Which component is faulty? So that I don't know yet. We'll have to do some more troubleshooting. Now let's see if I can adjust the voltage on this module. Get some tool in here. Hey, look at that. Yep. It is adjustable. So if I can go down to 12 volts here, see if it settles in. Hey, that looks pretty good. I mean, that's a very stable output voltage. No problems with that. So let me continue doing some more investigation and see if I can locate where the actual problem is, but it is nice to see that the power supply can actually function. Oh, let's look at this other output here and see if we have a voltage on this other module here. It's making a little bit of a vibration there. Let's try this. Yep, 8 volts. Looks very stable, no problems there. So, all good to see. So let me continue on with some more troubleshooting and kind of looking at this area and see if I can narrow down which component is actually giving us a problem. Alright, while the power supply has decided to cooperate, let me take a reading on the AC input to both of these modules. Be curious to see what the value actually is. So it should be an AC voltage at 100 kilohertz or close to that value, but I don't know what the voltage is. There's no specifications of what that voltage actually is coming into these modules, so let's find out. So go to AC voltage. So I'll just go across the supply rails coming into this module. Polarity of the probes doesn't matter. So yeah, look at that, 81.3 volts. So fairly elevated AC voltage. You wouldn't want to come across, in contact with those supply rails, and that's being regulated all the way down to 12 volts DC. Although this can go up to as high as 24 volts DC output. So let's check the other module. So 36 point, just shy of 36.2, 36.1918. And it makes sense that this is a lower voltage because this module only goes up to about 12 volts, maybe as high as 15 volts, but it is a lower output range than the other module, and this does have 2 secondary windings, so it makes sense that they're different voltages. So let's check the frequency. So 93.99, about 94 kilohertz. So it makes sense, I don't see any issue with that. So just a little bit under that 100 kilohertz. And the data sheet for this power supply mentions the 100 kilohertz. That's how I knew what that value should be. But again, they don't actually mention what those voltages are on those rails coming into the modules. So interesting to find that out. So we know that warming this circuit board along the top edge with the heat gun was able to make the power supply start to function. So that could be an indication of a broken solder connection, or maybe a component that has become thermally sensitive. So I figured to do any additional troubleshooting, I really needed access to the board as you see it sitting here, because this side is sandwiched up against these capacitors and there's no access otherwise. So there's only 5 electrical connections from this board over to this circuit board. So you see I've made those connections with these jumper wires, just soldered them onto the pins, and then you can see they're on the bottom of the circuit board on the solder pads. I need to be careful with this setup because there's over 300 volts DC potential in those 2 wires. So as I was doing the troubleshooting, as you see everything sitting here, I started to just notice that on this hole right here, the second one over, and there's a surface mount resistor right here, there was a spark occurring on the circuit board. So this is a plated through hole, and there's a trace on the other side of the board, and then this little surface mount resistor right here, and then there's a trace. Very, very close proximity to each other. And there might have been some contamination on the board from this leaking electrolytic capacitor. But whatever the reason, that sparking obviously shouldn't be happening. So I'll go ahead and put a magnified view on the video now, and you can see where that was actually happening. You can actually see the little dark carbon trace. And then I'll put a short video clip of the spark actually happening. Just look in the center of the video's frame and you'll see the spark. So now the circuit board is all cleaned up, the spark is no longer happening, but it didn't have any effect on the power supply's inability to start up. So much like this capacitor is kind of a side detour, and it really had no effect on the problem. So now let me show you what I found out. I'll go ahead and turn on the power supply. I'm going to switch on the isolation transformer. Alright, so it is turned on, and you can see we have a little bit of fluctuating voltage over here, being measured on that module right there. And the fan is sort of vibrating, shaking back and forth a little bit. Now check this out. So I'm going to just hold this over here just to support things carefully. I'm going to push down on the circuit board over here. Look at that. There it is. Now it comes to life. So it really looks like there is a broken solder connection somewhere on that board. Now of course the question is, where is that at? So continue with the troubleshooting. Let me see what I find out. So once again, I had the transformer removed from the circuit board. So several reasons why I needed to remove it. The transformer has very low impedance through its windings, and as I was using my ohm meter to do testing on the board, I didn't want the low impedance of those windings interfering or affecting the readings that I was getting on the ohm meter. And as you recall, the transformer was mounted in this area of the board underneath right here, and there are traces that pass on this side of the board, on the back side here. I needed to inspect all of those and take readings across the board, so I had to get the transformer out of the way for that. And the transformer adds considerable bulk along with the other circuit board that it's mounted to, so just removing it makes it that much easier to handle this board, and you're flipping it back and forth and taking a lot of readings and so forth, so it makes it much easier. So after spending a considerable amount of time testing all of these components on here, both sides of the board, tracing all of the traces around, taking measurements, and don't forget, as I'm taking each measurement, I'm flexing the circuit board, seeing if it has an effect on that reading, because obviously it's not until the board is either warmed up, or which is basically causing the board to flex, and as we saw, pressing down on this side over here definitely has an effect on the operation of the power supply. That's when the fault occurs. So if I don't press on the board and I just take readings around on the board, it's really not going to show the fault. So very time consuming, and obviously a lot of components on here to go through. So let me show you what I found out. So on the circuit over here, there's basically 2 areas of the circuitry that are almost identical or mirror images of each other. So there's 2 power FETs, one on this side of the heatsink and then one right here, that do the main switching to the primary on the transformer. So if we look right here, there's an active device here, and then right here, this may be a transistor or maybe another FET, I'm not sure. This looks to be like a diode. It has a trace on one side, trace on the other, even though it has 3 little terminals on it, but I think that's just a diode. And then there are 3 resistors right in this area here. And if we look up here, the same thing is repeated. We have the same active device here, that diode right here, And then there's that resistor here and the resistor right here. And this appears to be the driver circuitry for this FET, which is on the circuit board right there. And then this is the driver circuitry for the FET that is soldered on the circuitry right here. Now this transformer appears to be part of that circuitry as well. It's definitely tied into this part of the circuitry that I'm testing, and I'll show you the fault that I found so far. So let me zoom back out a little bit, and you can see the display on the meter. Pardon the camera movement here. That'll work there. You can see the ohm meter. Grab the other probe right here. So if I can do this with two hands here, what I have to do is get on this little trace right here, and I will get on this trace right here, and it's all in the shot there. Yep. Okay, so you can see we have 10 ohms right now across this point, and I'll zoom you back in and I'll show you the component that I'm actually testing. So if I take the circuit board and flex it by pressing down on this far side, look at the resistance value. Look how it increases. And it doesn't matter where my finger touches. You know, I'm not influencing that by where my finger is touching the board. Just flexing that board down is causing quite a drastic change, and that definitely shouldn't happen. There's definitely something wrong there. Okay? So again, flexing the board in that manner is having the same effect as if you were to push on the other side of the board and keep this side rigid over here. Just zoomed back in here. Actually, I'm going to hold this up here. It's attached over there on these wires, so I can't really get much closer than this. Grab the probe right here. So in this circuitry, if we look, again, this circuitry here and then up here appears to be the same. And don't forget, I don't have a schematic for this, so I'm just going by what I'm seeing on here and the readings that I've taken. Right here, from this point to this point, there's a jumper on the other side of the board that just joins those 2 points together. So this circuitry is ultimately coming up here. And you can see there's a capacitor right here. This appears to be a ceramic type capacitor, and so is this one and this one right here. So this capacitor and its position in the circuitry is the same as this capacitor and its relation to these components up here. Well, this is the capacitor that I just took that reading across. And obviously it has a drastic effect when I'm pressing on the board. So a capacitor shouldn't have any resistance reading through it like that, certainly not 10 ohms. That would indicate basically a shorted capacitor. Now, I'm not sure if the ohm reading that I'm getting is due to something else in the circuit, and that is a concern right now. I can't for certain say that this capacitor is defective, but this point in the circuit has a very large change in the reading. But if I come down here and measure across this capacitor, okay, I'll do that now, it does not have that same effect when the board is flexed. So let me zoom you back out again. Okay, so I'm going to go across this other capacitor, just like so. So first of all, you can see it's a much higher resistance at that point in the circuit, just shy of 50,000 ohms. And if I press on the board, very stable. Seems like it might have the slightest change there, but it's really more just the probes shifting a little bit on the pads there, the solder pads. I mean, that's very stable. That really has no effect whatsoever. So I'm sure that that's how the circuit should be behaving, on that other capacitor. Let me zoom you back in just a little bit again here. So again, this capacitor right here, the reading across it, no effect when the board is flexed and the resistance is quite high. The resistance is very low across this capacitor. The circuitry appears to be the same on both of those capacitors, how they attach to these active devices, these other resistors over here, and then ultimately to the power FETs. So I think the next thing that I need to do is actually desolder this capacitor and then possibly this one as well. I took a capacitance reading with my in-circuit capacitor tester on this capacitor, and it reads about a half microfarad, so the standard value would be a 0.47 microfarad. So that's a common value. I mean, that makes sense. This capacitor has no capacitance reading at all. It can't, because the resistance is just too low. It's affecting the reading. And this one right here, this capacitor, I'm not sure what its effect is. I do get a reading across it, but it's different again. And again, I'm not sure on the circuit how this is tied into everything else just yet, but the reading is stable across this other capacitor. Now, if I come up here to some of these other components that come over to this power FET, like these resistors up here, you do see a fluctuation when the board is flexed around. The reading changes, but it changes more at this capacitor. By the time you come over here in the circuit, it's a little bit different, and this part of the circuit is tied to this capacitor, and that's part of the problem of testing this in circuit. This could be maybe another component could be defective. It may not be this capacitor that's defective, but based on the readings I'm getting, it seems like the biggest change is happening right here. So I think it's worthwhile taking this capacitor off of the board, measuring it out of circuit. If it has a very low resistance across it, that's a definite indication it's defective. And if that's the case, I think this capacitor should also be removed and taken out of circuit and then measured for its value, and then I could just replace both of them. I think taking this one out of circuit and handling it, it would be wise to just put a new one in its place. I'll keep it as a spare if it checks out okay, but I think that will be the next step, is to start by removing this capacitor and then possibly this one as well. So I will do that, and then I'll be back and I'll show you what I found out. Okay, I've removed the two capacitors. So the capacitor that was positioned right here, where I was measuring that low resistance and it was changing when the circuit board was flexed, that is this part right here on the piece of paper, so a little speck right there. And then the capacitor right here, I believe, is identical to this capacitor based on how the circuit is designed, so we'll take some measurements on that as well and use that as a reference for the replacement part, so we know what value to replace it with. So let me show you what I found out. So again, this is the capacitor that was having that low resistance reading across it on the circuit board. So if I go in here with the probes, go across it here, and check that out. So about 87 ohms, 89 ohms, 87 ohms, right around there. So that capacitor has completely failed. It's turning into more of a resistor than it is a capacitor. So very, very leaky. And of course, a good capacitor should basically have an infinite reading across it. And we'll compare the other capacitor in just a moment. So let me use my LCR meter, and we'll take a reading on the capacitor as well. So move this piece of paper over here. So you can see the LCR meter actually does detect capacitance, and it is indicating 446 nanofarad. So 446 nanofarad would be the same as 0.446 microfarad. So basically the standard value would be a 0.47 microfarad, and that makes sense. So now let me grab the other capacitor right here, and so now I'll take a resistance reading across this one. So you can see we're immediately into megohms, and it's climbing, and then it just goes to overload because it's beyond what the meter can read, and that's perfectly normal. So what's happening is the capacitor is charging up, so the resistance starts low and then it climbs up, and then this tops out in the gigohm range, and it's no longer able to read any resistance through it. So that's perfectly normal. So this capacitor appears to be in good condition in that regard. Let's take a reading across it with the LCR meter. And 480 nanofarad, 479.5 nanofarad, right around there. So that makes sense. That's very close to the other one's value as well. So that would be a 0.47 microfarad. So that appears to be the correct value. So I will need to order in some capacitors. I don't have any of this type, surface mount style, and that value. So 0.47 microfarad would definitely be the type to go with. So I'll go ahead and replace both of those just because this one's already been pulled off the board, and might as well just put a new one in its place. Now, I don't know the voltage rating on these, but I'll make an educated guess. I believe it's probably around 50 volt or maybe 100 volt, but I think 50 volt capacitors would be perfectly fine. Just looking at the circuit and how they're being used, I don't believe they have a real high voltage across them. So let me put this back over here, and let's take a look again at the circuit board. So that issue with the resistance reading changing when the board was flexed now. Get the probes back on here. So now you can see, so make sure I'm right on the same part right there. Okay, there we go. So now that same point on the circuit, instead of being that very, very low value, you can see it's at 100 k ohms. And if the board is flexed, I'm pressing down, very stable reading. So all of that random low resistance and changing when the board was flexed is completely gone. So that looks very good at this point. I don't see any other issues going on with the circuit board. Like I said, I've gone through all of the other areas and they seem to be fine anyways. It was only in this one area, and I took some other readings over here and everything looks normal and very similar to the other circuit down here that looks to be the same design. I'm getting very similar readings now. So I think that capacitor was the source of the problem. So it's interesting. Let me grab this faulty capacitor right here, and these two safety capacitors and the electrolytics. So far in this power supply we have 3 very different types of capacitors and all have failed. It's always a capacitor. So I'll get those new surface mount capacitors ordered up, and I'll be back when those are here and we'll get those installed. The new surface mount ceramic capacitors are installed. So you can see this capacitor right there and the other one right there. And I also installed the 2 safety capacitors right here. So these are a different brand than the originals right over there. So these are made by Samsung, but they have exactly the same electrical ratings, so a direct replacement from the originals. So the next thing that I'll do is install the transformer back on the circuit board, and then let's do a test setup and see if the power supply has come back to life. Alright, the assemblies of the power supply are connected together. The fan is plugged in. I have it plugged into my isolation transformer, but it's not turned on just yet. And the digital multimeter is connected to this module. So let's see if the power supply works correctly now. Alright, I'll switch on the isolation transformer. Let's see what happens. How about that? No problem. So we have output voltage, looks very good. Fan is running. And so far so good. So what I'm going to do is let the power supply run for a little while like this, and I'll cycle it on and off a couple times. I'll press on that circuit board, kind of flex it around a little bit like I was doing before when I was troubleshooting, just to make sure that there are no other intermittent problems or that the problem doesn't come back. And if everything looks okay, then I'll put it back in the case and we'll run a full load test on the power supply and make sure that it's able to meet the rated outputs of each module. Okay, the circuit boards are back together. So now I'll take this assembly and install it in the bottom part of the chassis, and then the modules will get installed back onto this circuit board, and then the top cover can be installed along with the fan piece right here, and then we can power it up and do the full load test on it. So there's 2 ways to deal with these output modules. You can pre-install them on the circuit board, and then this whole assembly can be installed in the bottom half of the case. Or as I've done here, you just remove this plastic pin out of the circuit board, and it allows this insulator sheet to be removed off of this board. And that gives you access to the holes across here where the screws go through, and of course that's what attaches to those modules. That's the electrical connection off of the secondary of this transformer. And don't forget to apply some thermal compound to the bottom of each of the modules. There's a power rectifier that's in here, and it needs good thermal transfer from this portion of the module down into the bottom of the case right here for the heatsink. And this is an example of what I use for the heatsink compound. Alright, let's do a load test on the power supply. So I have the line cord connected. These heavy gauge wires are going up to my dyno load. Now it's on the second shelf above the workbench, and I can't get everything in the same shot with one camera. So once the load test is underway, I'll use a second camera, and I'll just inset a shot of the dyno load in operation, just so you can see that piece of test equipment. So these test leads that are clipped on right here are going over to the Fluke 289, so that'll monitor the output voltage. And I'll start with the G module, and I've set it to 24 volts. and then the C module is set to 12 volts, and we'll test the C module second. So the G module is rated up to 15 amps. So 15 amps at 24 volts will be 360 watts. This is a 400 watt power supply, so that'll put a good amount of load, on the power supply, so that'll be a good test for it. And this is a Fluke I410 AC-DC current clamp. So for every amp that it measures, it outputs 1 millivolt. So if you're measuring AC current, this outputs an AC voltage, and if you're monitoring DC current, which we're doing here, this outputs a DC voltage. So on the Keysight 34465A, it's set to DC millivolts. So if this is measuring 1 amp, then we'd see 1 millivolt. So this is millivolts and then decimal point and then hundreds of microvolts. So when we're up to 15 amps, this will say 15 millivolts over here. All right, and the fan that you hear running right now is up on the dyno load. So you're going to hear the fan kick in on the power supply now when I turn it on. All right, so we have output voltage. That looks very good, 24 volts. So let me switch on the circuit breaker on the dyno load. And I'll start to increase the current. So let's go up to about 5 amps. Right about there. That's pretty close to 5 amps. And voltage is holding up, no problems there. And we go all the way up to 10 amps. Let's try that. Alright, so 10 amps, so 10 millivolts is 10 amps. And voltage is still holding up. Looks no problem there with the regulation. Very stable. And let's go all the way up to 15 amps. There we go. So 15 amps, and voltage is looking very good. So I'll switch the dyno load off and then back on. So when it goes off, the voltage holds pretty steady there. No major fluctuations or drifting or any problems. And I'll switch it back on. Right at 15 amps and no problem with the voltage. So that's looking very good, no issues whatsoever. Now you may be wondering why I use this current clamp over here instead of just running the current through the digital multimeter. The digital multimeter, whether it's the Fluke or the Keysight, it tops out at 10 amps that you could put through those meters. So I didn't want to, of course, blow the fuse because we're going to 15 amps. So I needed to use a current clamp. You could also use an external current shunt, but I don't have one of those. I typically use current clamps. Okay, I have the connections moved over to the second module, and I set that module to 9 volts, so let's try it out. Power supply is turned on, and 9 volts, looks good. So I switch on the circuit breaker on the dyno load, and then I'll increase the current. Start with, let's say, 3 amps. Alright, so 3 amps, and voltage is holding up, no problem there. Try 6 amps. That looks very good. And let's go all the way up to the full output current on this module, which is 12 amps. Alright, so there's 12 amps, and voltage is again holding up, no problem there, looks very good. So I'll switch off the dyno load. Voltage holds steady, no problem there. I'll switch it back on. Picks up the load, no problems with that either. So the power supply looks like it's functioning very well at this point. So the repairs on the Omega MML 400 switch mode power supply are now complete. The power supply is functioning very well, and it's definitely ready to put back into use. So these are rather expensive power supplies, so it's definitely worth the time and effort to make the repair. And the cost of the replacement components, in this case several capacitors, was quite minimal. So it keeps the power supply out of the landfill, and it should be good for many more years. So if you enjoyed this video, please remember to give it a thumbs up, and if you're enjoying the videos on this channel, don't forget to subscribe. Tap that bell symbol to be notified when I post a new video. There'll be many more videos coming up in the near future, all things electronics, tech talk videos, how-tos, repairs, test equipment, audio equipment. You won't want to miss any of that. So until next time, Take care, thanks for watching, and goodbye for now.